All right, guys, how we doing today? Today I'm just going to be doing a video, just going over trusses today. I don't plan on doing videos like this in the future. I'm not sure exactly what I'm trying to do yet. I'd like to get a marker board here and do it kind of like a normal tutor session. I think that'd be a lot better. We can do some, in the future, if I can get it to start working, I would like to be able to have live feedback, so you guys can have like a live session. I was hoping more of my teachers would do that, but as of now, I don't have any professors that are doing it, so that's kind of why I waited to get this video out. Wasn't sure exactly what they were gonna do, kind of wanted to follow that same format, but as I can see now, everything is mostly videos. All right, so let's just jump right into trusses. So first off, when we look at a truss, what exactly would you think of as a truss? Okay, so this here is what I would say is a truss, okay? We have multiple members, okay? And all these members here are supported by pins. You see that? Okay, now in reality, is that what a truss looks like? Not quite, okay? So we're gonna simplify these trusses. In reality, a real truss is gonna have a plate here, okay? And this plate is gonna have these members bolted into the plate, okay? But just like we've always done in statics, we take something complicated and we reduce it down into something that is a lot more simple, okay? And the way that we're gonna do it today is exactly like that. We're gonna make the assumptions that all loadings are applied at the joints and all the members are joined together by smooth pins. Okay, that should sound familiar to everybody, especially from the last exam. What does that mean? That means that everything is a two-force member, okay? If you guys have not seen this before, this is the study guide. I believe I sent it out to everybody, okay? This here is the only reason I got an A in this class, and I swear 100% by it. I reference it all the time, okay? So we're gonna be using that quite a bit here in this tutoring session, especially because you guys, if you guys are looking through this, you can follow along. So what I would recommend is reading this here, okay? Assumptions for design, okay? And then here, we have the methods that we're going to be able to use to solve these. Methods of joints, okay? And methods of sections, okay? So 6.2, 6.4, very important, okay? I'm not gonna elaborate like mainly on those like right now. I'm just gonna kind of like walk you through them in the way that I solve trusses. I mostly believe in method of joints. Methods of sections is faster, but it gets more confusing in the aspect of I just personally don't like it. I'm not saying it's a bad method of doing it. It's faster. If you can get it down, it'd be a great option. I personally just don't like it. Okay, so we talked about kind of what it looks like, okay? Now let's talk about where we start, okay? So if we have something like this, what do? Okay, well, we're gonna draw a free body diagram, okay? So right here, I have a blank version of the same truss kind of drawn out, okay? We have two external forces. And what is a free body diagram? Free body diagram is the member that we're interested in, or like, you know, the area, the control surface, everything like that. So what we say is this control surface or this area or this member or object is this overall truss. Now we gotta say, what are the external forces that are acting upon it? Okay, we have this force here, okay? But we have two support reactions that connect our member to the outside environment. So we have to analyze those as well. Okay, so we have pin A, which is a roller. Excuse me, I'd call it a pin. Okay, and over here we have H. Okay, so we're gonna analyze both of these. This one here, we can slide back and forth. We can analyze the roller pretty well. We can lift it, but we can't bring it down. So there here is an AY. I'm gonna assume it's positive, okay? Over here, we have H, okay? We know that this is connected by a pin, so we can say that we have some HX and we have some HY. Okay, pretty simple, done it before, not a big deal, okay? But when we look here into our problem statement, what's the first thing it asks for? It says identify all zero force members. Perfect, well, what is that? Okay, so if we go back to our handy dandy little thing here, it's got, right here, trusses using zero force members, okay? So they're usually determined by inspection of each of its joints, Okay. This first part here says if only two members form a truss joint and no external load or support reaction is applied to the joint, then the member must be a zero force member. Okay, now what does that look like? Okay, so it says two members that come together to form a joint. So the way I think of it is something like this. Okay, and at the intersection of this joint here, there is no forces here, or here, or here. Okay, there's nothing acting at that joint. What does it say about these two members? Okay, it says that these members both support zero of the load. There is nothing between those two that actually do anything to help the truss out, okay? Now, a way to think about that is we've just said that all these members are two-force members, okay? So what we're going to do is we're going to say, hey, this here is point A, this here is point B, this here is point C. Okay, now let's redraw this as two-force members. Okay, so what happens if we draw here, we have, let's go FCB, okay, and then here at B, we're going to draw back in the same direction, and we're going to use the same terminology to describe this other half of this. This here is also FCB, okay? And why are those labeled the same? Because they're the same force, right? Like we said with two force members, all that means is that the forces are constant throughout the member, okay? So if this is equal to that, might as well call them the same thing. Let's not get confused, okay? So then we also have this member that comes over here, okay? So this is FBA, and this here is also FBA, okay? So now, if we look here, we don't know much information about these, right? So let's kind of neglect these for now and just draw this pin right here, which is pin B, okay? So let's redraw pin B, okay? If we have this FCB, well, I'm sorry, I don't know if you guys can see that. All right, I think you guys are on camera now. Okay, if we have FCB and we have FBA, keeping the same terminology, let's do some of the forces about this point, right? We know from statics that this point here, or this joint, has to be in equilibrium. Some of the forces in the y are equal to 0, which are equal to, let's just say that this here is 30 degrees. Okay, so how do we find this? Let's just say that F, well, hopefully my pen's not quitting on you guys, FCB sine of 30, okay, what else do we have in the y? We don't have anything else in the y, right? Okay, so then we can say that FCB is equal to 0. Okay, now let's do some of the forces in the x, which are equal to 0. Excuse me. Okay, so we have negative FBA minus, okay, because we're going to say, hey, this is positive, this here is positive, all right, minus FCB, and then we're going to say that this here is cosine of 30, okay? Well, if we know this here is 0, then we know that FBA is equal to 0. Okay, do we see that? That is the first way to determine a zero force member, okay? If two beams connected by one point have 0 external forces at that point, then both of them are 0, okay? All right, so let's move on. There's another way to do it, okay? Here it says if 3 members form a truss joint for which 2 of the members are collinear. the third member is a zero force member, okay? Provided that no external force or support reaction is applied to the joint. Okay, now what does that mean? Okay, so first, two collinear beams, okay? Here is two collinear beams, okay? This is beam 1, this is beam 2. So this is A, this is B, this is C, okay? Two collinear beams, and then there's a third that come from the point in the middle, okay? So let's just say this here is point D, okay? If there is no force here, or here, or here, okay? No force, then this is a zero force member, okay? Or it's saying like, hey, two collinear beams and there's a third member, okay? No force of the joints, third member is always zero, okay? That's the second way that sorry, I bumped you guys. That's the second way that we can find zero force members. Okay, so I can do that real quick. What we're gonna do is we're gonna split everything up, okay? This here's a two force member, this here's a two force member. This here's also a two force member, okay? So we're gonna look at the point right in the middle that has all three members, okay? We're gonna do point B, just like we did before, but we're just gonna do it a little bit faster than we did last time, okay? So B, we're gonna have FBC this way, and we're gonna have FBA this way, okay? And over here, we're gonna have FBD, okay? Just like we did the last time to prove this, we're gonna do a sum of forces in the X and sum of the forces in the Y, okay? So sum of the forces in the X are equal to 0, which are equal to FBA, which is negative because it's going to the left, plus FBC, okay? So right here, we can say that FBA is equal to FBC, okay? All right. Now, let's do that for the sum of forces in the Y, okay? We're gonna say that up is positive. Sum of the forces in the Y are equal to 0, which are equal to, okay? The only thing that we have here, I screwed this up, okay? I'm sorry, because let's say that this here is 30 degrees. Okay, so we're gonna have negative FBA plus FBC minus FBD cosine of 30, okay? So right there, we can't solve anything from this equation, right? Because we have three unknowns, okay? And this is just trying to show that this equation isn't going to work, okay? So in this equation, the only thing that shows up is negative FBD, okay? And this negative FBD sine of 30, okay, is the only thing in this equation, then we know that FBD goes to 0, right? It cannot be there, okay? And that's saying that if there's something in the Y here, there has to be something in the Y there, correct? It would have to be in equilibrium. Okay, so those are two ways to find zero force members. So if we go back to our original truss, okay, well, not that one. If we go back to our original truss and we look here, okay, we're gonna have to figure out if there's anything that solves those two scenarios for zero force members, okay? So what are those two things, okay? So if we have two members that come like this, right, to a point, and there is no forces here, it just looks like this, okay? Both of those are 0, okay? We're gonna look around. Okay, where do we have just two members coming together? Here and there, okay? Do these two have forces at the points? And I would say yes, they definitely do, okay? And those members cannot be zero force members, okay? So now let's look for a scenario that has two collinear beams, so like this, two collinear beams that has a third attached to it. Okay, now is there anywhere on this that we have that? Well, the only ones I can think of, two collinear beams, and a third off of it is here. Two collinear beams, and a third off of it is there. Okay, now, are any of those zero force members? Okay, so what is gonna tell us that? Is there any forces at this point here or this point here? Okay, now we look. Okay, right here, there is an external force. So this cannot be a zero force member. Why? Because if we did some of the forces in the y and some of the forces in the x, well, x, y, right? We can say that this from here to there will be going to the left or to the right. This one here will be equal and opposite. Okay, they can cancel each other out. Now, if this one's going down, this one has to go back up. We see that? Okay, so that cannot be a zero force member. Okay, so now we go over here. Look at this point right here. Okay, we have something to the left and we have something to the right. Chances are those two can cancel each other out. But if we have something going up or down, okay, there's nothing here to cancel it out. So we know right away that this here is a zero force member. So if we look at the problem statement, okay, it wants us to identify all zero force members, okay? And right here, I went up and put a 0. And right here, I said it was FG. So maybe I should plot some points on this, huh? So I'm going to say A, this is B, this is D, this is F, this is G, this is E, this is C, okay, that's H. All right, I think we got all the information. I apologize for that, okay? So for the zero force members, okay, we're going to have the member FG, okay? And these members are denoted by a bar, but that does not mean that they're a vector. It's just saying, hey, that's the member there, FG. Okay? All right. Now, let's look at what else they want. Okay, so it says draw an appropriate free body diagram. Well, we've already done that, right? We've already said, hey, we know exactly what to do. Okay? Determine the force in the member AB and indicate whether it's in tension or compression. Okay, so when we think about external forces in this section, now what are the possible, or internal forces, excuse me, what are the possible internal forces we can have when we think about these trusses? Okay, so if we know that all of these are two force members, and we all know that the force is constant throughout, do you think we're going to have shear forces or bending moment forces? Which we haven't really talked about in this class yet, but they're coming for this exam, okay? And the answer is no. We will only have axial loading, which is in tension or compression. So when we think about it, if we take this pin here and we apply a force here at the plunger, and we apply a force here at the tip, all right? And we push those two together, this member here would be in compression, okay? And if we grab this member and we pull on it, it would be in tension. So it wants us to determine whether the member AB, A to B, is, or what is the magnitude of that force, and if it's in tension or compression, okay? So how are we going to do that? Well, first off, when we look at something like this, the first thing that we do for like a framer machine is draw a free body diagram. What's the second thing we do? We're going to find these support reactions, right? And this is where I think a lot of students get tripped up, is they want to take this stuff apart, right? They see all these two force members and they just scream right away, let's take the sucker apart. And we do not want to introduce more unknowns, okay? Let's see if we can solve these, okay? And what are the ways that we think that we could solve these, or the easiest way, okay? So how many unknowns do we have? We have 1, we have 2, we have 3, okay? We have 3 equations. We have sum of the moments, okay? Sum of the forces about the x, which are equal to 0. We have sum of the forces in the y, that are equal to 0. Okay? So, how do you think that we're going to start this? Okay, so we have 3 unknowns, 3 equations. Okay, but we look real quick. I think we need to start with a moment. Okay, now about which point? Should we take a moment about A? Should we take a moment about H? Does it matter? Okay, if we take a moment about A, we know that AY falls out of that equation. Okay, but if we look at HX over here, HX will also fall out. Why? Because its line of action also passes through A. Okay, so it doesn't really matter. So for simplicity, we're going to solve about A. Okay, knowing that AY and HX are not going to be in this equation. Okay, now we can solve for one variable that we will call HY. Actually, I apologize. On my my test I did here, I said that it was some of the moments about A, but I take that back. We're going to do some of the moments about H because that's actually what I did. Okay? Just so I don't have to redo the math for you guys. I don't think you guys really care. Okay? So what we're going to do, and I also apologize that each one of these here is 3 meters apart. 3 meters, 3 meters, 3 meters, 3 meters. Alrighty. So now let's do some moments about H. I apologize. Okay? So we're going to go from H, go out to our first force here. Okay? This first 4.5 kilonewtons is going to cause a moment in this direction. Okay? So now if we use our right-hand rule, we can put our thumb about our point H, okay, up or down, lay our hand across perpendicular distance, which is this 6 meters, and curl our fingers in the direction of the force. Okay, so we know that that there is a positive moment. So we're going to say that that is equal to, okay, 4.5 kilonewtons times 6 meters. Okay, and if we do that there, we have a positive moment about HY. Okay, and that there is kilonewtons times meters, right? And that is a moment, okay? We also are going to have this here plus 2.7 times 9. And that there is going to be kilonewton meters, okay? Minus AY times this perpendicular distance of 12, okay? And it's negative AY because right-hand rule, we put our thumb along the z-axis at our point H, okay? We lay our hand across perpendicular distance and we curl in the direction of the force. So we know that that is negative. From this equation, we know that AY is equal to 4.28, okay? And it came out positive, okay? Because we add AY over, divide by 12, it comes out positive. So we know that AY is 4.28 kilonewtons, and we also know that it is up, okay? We've assumed correctly. Okay, so now we're going to do the sum of forces in the x. Okay, and if we do that, we can say that we have hx in that x direction, and we have nothing else. So we know that is equal to hx. We know that hx is equal to 0. Okay? So now we can do some of the forces in the y. Some of the forces in the y, we have our ay, which is 4.28. That's kilonewtons, and that is up. Okay, we have hy, which is also up, so that would be added, minus 2.7 kilonewtons, okay, minus 4.5 kilonewtons. Okay, so we know that hy is equal to 2.92 kilonewtons up. Okay? So now what do we do with that information? Okay, so now we know these things here. So what I would do is just bring them up into our diagram. Okay, it's gonna help us visualize something a little bit better, okay? Which is equal to 4.28 kilonewtons. That's AY. Okay, now we're gonna go down here to HY, and we're gonna say that there is 2.92 kilonewtons. Okay? Now we're gonna look back at what they want. What do they want? Determine the force in the member AB and indicate whether it is in tension or compression. So if we look here at AB, okay, we want to start with the place with the most knowns, okay? So if we were to go method of joints, we could go one of two ways. We're going to start with the most knowns. So in this case, the only knowns that we have are here, 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 and there. Okay? And I would suggest mostly all the times we're going to solve for AY, HX, HY, and we're going to start from one of those 2 points. Okay? And which direction that we're going to start in depends on what's we want to find and where it's closer to. Okay? So in this case here, we have A, B, and we want to find the force between these two right there. Okay? So what I think we should do is redraw this here by splitting this 2-force member and this 2-force member. Okay? So what we can do is just draw point A. Okay? And then off and to the right, we can say, hey, this here is FAV up and to the right, and we have here FAC, which is straight to the right. Okay? Here we have AY, which is equal to 4.28. Okay? And in this case here, do we know what direction FAB is or FAC? No, we don't. Those are just assumptions. Okay? So, one thing we can do is say, hey, we're going to go up and to the right because, hey, positive up is sign convention, and positive to the right is sign convention. And we can say that this is to the right because that's sign convention. Okay? However you guys want to look at it. But I hope you guys see right away that, hey, if FAB is up and AY is up, there's going to be a net force up that is going to move this point, and that cannot happen. Okay? So, if we were smart, which Taylor was not, I would have known right away that FAB was in the other direction. Okay? So now that we've looked at it a little bit, let's get rid of this point right here and say that FAB is down and to the left. Okay? I hope you guys see that. Okay? And this angle between these two is 30 degrees. So what I'm going to do is say this here is 30 degrees. Okay? I hope we all see that. Okay? All right. So now what I'm going to do is do some of the forces in the X and some of the forces in the Y. Once we get into internal forces, we're not going to use the moment equation. Okay? So right now we're limited to 2 equations. So if we do some of the forces, where do you think we should start? Should we start with some of the forces in the X or some of the forces in the Y? I think we need to start with some of the forces in the Y because we have this known, right? We're going to start where we have the most knowns. Some of the forces in the Y are equal to 4.28, okay, minus FAB, and that there, Y, is going to be sine of 30, okay? All right. So now we know that FAB is going to be a positive 8.55 kilonewtons. Okay? Now, what do we do with that information? Well, that there is a positive value. So what does that mean? That means that we've assumed correctly. We know that FAB acts up and to the right. Okay? Oh, excuse me. Not up and to the right. Down and to the left. Down and to the left. Excuse me. Okay? Now, we look here. That's what it wanted us to find. Now we have to indicate whether it is in tension or compression. Okay? So now what I'm going to do is I'm going to draw point A and point B. Okay? So if we look at point A, which we have right there, we're going to redraw that, saying that we have this member here, down and to the left. We have this one here, to the right. Okay? We know that FAB, this is A, we know that FAB is solved for and it is down and to the left. Okay? So now, let's draw point B. Point B is just the continuation of this line here, okay, until we get to here. Now this here is also FAB. Okay, if this one's down and to the left, this one here has to be up and to the right. Agreed? Well, I sure hope so. Now, if this is up and to the right, okay, we have to know what, or let's just finish drawing point B. Okay, so we have a vertical member off there, and we have a horizontal member off there, okay, and then we have another horizontal member, or not horizontal, but slanted member up that way. Why? Because there, and there. So this here is FCB, this here is FBE, this here is BD, okay? Because this here is point B, okay? I hope everyone sees that. I hope it's not too awful messy for you guys. All right, so it wants us to know if this member, FAB, or this member, A to B, is in compression or tension. Okay, so now how are we gonna analyze that? Okay, so we know that that FAB is here and here. Okay, here is A, here is B, and here is FAB, and here is FAB. Okay, now is this in tension or compression? This is where it gets really tricky. Okay, so first off, we have to think of, are these external forces or internal forces? Okay, and I hope you guys are all screaming that it is internal forces. Okay, so now let's just look at a normal situation where we would have a beam in both compression and tension. We talked about it earlier, right? We have that pin that I had in my hand, still do, okay? And I apply two forces in this direction, okay? Now, is this beam in compression or tension? Okay, this beam here is in compression, okay? Now, what does that mean for us? Those are external forces causing this beam to be in compression, okay? So we know that this here is connected by two pins, right? And the forces act on the two pins, okay? So we know that this here is a two-force member. So what we can do is draw a beam that is cut in half, okay? If I have a force in this direction and I have a force in this direction, the beam is in compression. But from the internal forces side, I have a force opposing this, and I have a force opposing this. So what does that mean? That means that this here is in compression, okay? I hope that makes sense to everybody. It's a little bit goofy, but what it's saying is there's two external forces causing this to be in compression, and the two internal forces oppose both of those. So we're looking at internal forces. So a way to think about it is if the internal force acts towards the pin, that member is in compression. Okay? Because the internal force is pushing on the pin. Yeah, you just kind of got to think about it like that, right? Because it's resisting the external forces that causes the beam to be in compression. Okay? I hope everybody gets that. That is huge. Okay? And it's probably worth to note now that compression is denoted by a negative sign. Okay? And what we're going to say is when we find a beam that is in compression, we're going to say that it is so many kilonewtons or newtons. We're going to say it's compression, and we're going to throw a negative sign behind it. And that does not become super important right now, but this exam, that's going to be one of the hardest things, is to talk about sign convention. Okay? We know that equilibrium equations, if we get a negative outputted from it, all that means is that our assumption was incorrect, right? So we never throw a negative in front of a value and just put units behind it, right? We're going to assign sign convention with the understanding of what causes that sign convention, okay? And I don't know if your professors are going to follow that or not, but I think that is very important. We're going to do sign convention with our understanding of what it is, okay? Because negatives and positives are all kind of horseshit, right? Okay, so now we know that this member FAB is 8.55 kilonewtons. We know that they're acting towards the pins, right? They're resisting some compressive load. So this here is in compression, and we're going to say that this here is negative, okay? Like I said, right now it's not a big issue, but later on, it's very important that we know that tension is positive and compression is negative. Okay, so if you guys want, I can draw one of these examples real quick for tension. Okay, we can say that if we're pulling on the beam here and we split it up, excuse me. Okay, and we split it up. And we have an external force pulling here, external force pulling there. We have internal forces acting like this, okay? And if we drew that kind of in the same way, saying, all right, we have a force pulling here, and we have a force pulling there, okay? This here would be in tension, and the way I think about it is if I'm pulling on that pin or that joint, it's in tension, okay? A little bit goofy, but this here is in tension, and that there is positive. This here is in tension, and that is positive, right? Sweet. Hope you guys are all following. Okay? All right, so now let's look at what else that they want. Okay, so we've decided if it was tension or compression. We said that it was in compression. And then for this problem, it's not really important that we know that compression is negative, but in the future it will be. Okay? Now it says determine the force in the member FBD or just the member BD. Okay? And indicate whether it is in tension or compression. So now that's where we look at what knowns we know, okay, and where we're going to have to go to solve for that. Okay? So we think about our knowns. We have AY, we have this known, we have that known. Okay? Now, how are we going to decide where to go with this? Okay? Because right now, we've solved for FAB, but we have not solved for FAC. So that is one unknown that we don't know here. We also don't know this force here. Okay? If we don't know this force here, we don't know this force here, where do we go? All right? So we got to pick a pin that we want to go to next. Okay? So this here is a method of joints. Okay? Now, what I think we need to do is finish this problem out here and find this force here, FAC. Okay? because it might just be worth us knowing. Okay. Let's see what I did on my exam. I actually did not find that. I said it was negligible. Okay, you could find it, right? Wouldn't be the end of the world to find it, but we're not going to need it. Okay? So I think what we should do is just go straight up to point B, okay? And we already have a diagram of point B drawn right here, okay? And this is where I've been talking about updating our diagrams when our equilibrium equations show that we've assumed incorrectly. Why is that important? Because this diagram here tells us that this here diagram needs to be like this. And if this is up and to the right, we have to know more information about this to say what directions the other ones are. Okay? So this FAC is going to the right. So let's just say that, let's keep drawing this two-force member. Okay? And let's draw in our point C here. Okay? This FAC goes back to the left, equal to that. Okay? Now we also have this CB there, right? And we also have this about this FCE, okay? Also, off point C, we have this 2.7 kilonewtons here. 2.7 kilonewtons. Okay, now this is super important that we know that this goes off and to the right. Is the value important? Not really. Okay, but we know that if this goes off and to the right, these are going to be equal and opposite. Okay, now this and this are going to be equal and opposite. Why? Because these are strictly in the y, these are strictly in the x. So this here down has to be opposed by this FCB. Okay, and we know that those have to be down. Okay, we can prove that with some of the equilibrium equations, right? If we say that sum of the forces in the y are equal to 0, which are equal to, we have FCB minus 2.7 kilonewtons. Okay, that is for this free body diagram there. Okay, we know that FBC is equal to 2.7 kilonewtons up. Jeepers. This pen might be shitting out on me, guys. Okay, 2.7 kilonewtons up. Let me see if I can find another pen real quick. Now I got a marker, but I have to switch to that. Hopefully you guys can see this. That's why I'm doing it in a pen. Although I do not recommend doing this class in pen. All right. So now we know that FCB is up, which isn't super awful hard to grasp, but that means that this FCB is down. We know more information about this here. Okay, now what do we know about these two here? Okay, we don't really know anything about them. But when I see a force up and to the right here, and I see another force in that same direction, I'm just going to assume that it opposes it. Okay. So this one here is up and to the right. This one here, I assume it's down and to the left. Okay. This one here is strictly down. So I'm just going to put another assumption in there that this here is up and to the left. Okay. So now let's redraw this diagram here. We're going to redraw down here just so we can keep our sum of the forces equilibrium equations next to our diagram. Okay? So I'm going to say that we have this point here, which is point B. Okay? We have FAB. We have here FBD, And here we have FCD. And then here we have this FBE. Okay, like I said before, this is method of joints. We're starting from one joint that we have the most unknown, and we pick that first joint by what's closer to what we want to find. Right here, this A is closer to B, which we have all the information we need, right? All right. So we can say that we need to break these down into x components here. Okay? So we need to find these x and y components of these horizontals, right? And we can do that by just saying, hey, this angle here is 30 degrees, and we can say that this angle here is 30 degrees. Okay? We can also say this angle from the horizontal here is 30 degrees. Okay? Everybody's seeing that. All right. So now what we're going to do, we know that this FAB here is 8.55 kilonewtons. Okay, and we write it by our variable in the diagram. It means that we know that for a fact is up and to the right. Okay, because we have to know what our unknowns are. And we know that this FCB, okay, is also solved for, which is 2.7 kilonewtons. Okay, but if we look here, FBC says that it's up. Okay, now what does that mean to us? Is it was up for this diagram here. Okay, so what I'm going to do is just box this and say that that is for that equilibrium equation. Okay, so now it has to be equal and opposite, right? We're in this diagram. Okay, I'm sorry, this is kind of a mess. I just kind of want to keep it on this page because we have our diagram here. Okay. Now what? Okay, so I think what we can do is start doing some of the forces in the x and some of the forces in the y. Which one are we going to start with? What do you guys think? Okay, so what do we have the most unknown? Or where do we have the most knowns? Okay, we have this FAB, sine of 30. We have this FCB, which is in the y. We need to find FBE and FBD. Okay, so we have two unknowns. We need two equations. Okay, it doesn't really matter where we start, right? But I think what we should do is sum of the forces in the y. Okay, so I'm going to say that, hey, we're going to follow positive sign convention. Sum of the forces in the y are equal to 0, which are equal to, and let's just start and go left to right, okay? We have FAB sine of 30. We have negative, and we're going to put just substitute our value in, negative 2.7. Okay, we're going to have a positive FBE, okay, and that is also going to be, let's draw the uppercase E, FBE, and that is also going to be sine of 30, okay, and then we're going to have minus FBD, and that there is going to be sine of 30. Okay, so this would be a problem where we could say, hey, do we want to switch our axes, you know, and saying that these two are both in the same direction? And the only reason I would say, yes, you want to switch your axes, or no, you do not want to switch your axes, is what does the majority of the forces act up in? Or what would be the easiest to find? Okay, and the only reason that I would ever switch my axes in this case is if these were in the same direction and this was perpendicular. If this was 90 degrees off from that, I definitely would. Okay, but it's not, right? This is 30, 30. It's only 60 degrees off from the other axis, so it can't be a third axis. You'd have to do sine and cosine of a bunch of crap anyways. So might as well stick to what we know, right? All right. So we have, I did not substitute this in, which I should have. This FAB is actually 8.55 sine of 30, okay? We can't solve for this, okay? So we need another equation. So now let's do sum of the forces in the x, which are equal to 0, which are equal to, okay? We're gonna have 8.55 cosine of 30 minus FBE cosine of 30, okay, and then minus FBD cosine of 30. Okay? All right. Okay, so we look at this equation here. We have some of the forces in the x. We have this cosine of 30, this cosine of 30, this cosine of 30. What if we divide all of these cosines of 30 over to the other side, to that equal sign? Okay, that's just a little trick there. We can say that this cosine, when divided away, it goes away. 0 divided by cosine is still 0. Let's divide this cosine of 30 away. Let's divide this cosine of 30 away. See how that simplifies that really well? So what we can do is say that for the sum of the forces in the x equation, we can say that we have 0 is equal to 8.55 minus FBE minus FBD, okay? And what we can do is just substitute one of these into that other equation, okay? So let's say that